Hey guys, Physics in the Flesh is back with the fourth installment of relative velocity examples for two-dimensional kinematics. A swimmer is capable of swimming 0.54 meters per second in still water. A. If she aims her body directly across a 77-meter wide river whose current is 0.45 meters per second, how far downstream from a point opposite her starting point will she land? And B. How long will it take her to reach the other side? Okay, so we are going to solve this like the previous relative velocity problems, and that is that we're going to express the velocities in terms of x and y components. Since this is actually the more straightforward way to solve these problems, since it's more realistic. Okay, so first things first, let's define our positive direction. So we're going to let positive be up, that's going to be our y, and to the right, that's going to be our x. Okay, so next we have to define our three objects. Now, in this question, we have the water, the swimmer, and normally at this point, the last one we would call the shore, but I don't want two S's, and I don't want two letter subscripts, so I'm just going to call it land. Okay, so W for water, S for swimmer, L for land. There are our three objects. Okay, now let's start defining what we've been given in the problem. Okay, so a swimmer is capable of swimming 0.54 meters per second in still water. That is the velocity of the swimmer relative to the water. So VSW, okay, so that's equal to a vector whose units are meters per second. Now, the swimmer is moving down the river. Now, you know what, before I even fill in the vector quantities here, let's just do a quick sketch here of what's happening. So we've got our river. We are told it is 77 meters wide. So that is our width in the y direction. Just take note of that. The swimmer is trying to go directly across, right? Velocity of the swimmer relative to the water. At the same time, the water current is going down, right? So that's the velocity of the water relative to the land. So she's getting pushed down, and her net direction is going to be in this direction. That will be the velocity of the swimmer relative to the land. Okay, so now that we've got those three things established, take a look at this. The swimmer relative to the water, she's moving purely in the y direction. So the x component of her velocity is 0. And since she's swimming at 0.54 meters per second, that is going to be the y component. So 0.54 goes right there. Okay, next, the velocity of the water relative to the land. Again, put your brackets, your meters per second, put your comma. The x component of the water relative to the land, that's the speed that the water is going down the river. And based on the question, it says the current is going at 0.45 meters per second. So that is going to be the x component here, 0.45, and the y component will be 0. Now, based on this picture that we drew, based on this picture and just based on the problem itself, we can establish the equation that VSL, the swimmer relative to the land, is equal to the velocity of the swimmer relative to the water plus the velocity of the water relative to the land. And as we've seen in the other problems, in order for this statement to be true, the middle letters, you need to imagine them canceling out. And when they do, you're left with the outside two letters, which is exactly what we have here. Now, this question is a little bit different than videos 48, 49, and 50 in that the question itself is not asking you what's the velocity of the swimmer relative to the land. Okay, the only reason I even constructed this expression is because I was given these two values, so I know automatically that this I can determine, and whatever I'm looking for most likely is going to involve this quantity. Okay, so part A, if she aims her body directly across the 77-meter wide river, okay, how far downstream from a point opposite her starting point will she land? So we're trying to find the distance she's going to, so if she starts here, what distance does she end up in this direction? Okay, that's downstream. And downstream implies the x direction. Okay, so to find the distance downstream, we need delta x. So for a problem like this, we would assume no acceleration, Okay, we've got a pretty linear motion. So we've got a distance, and distance requires speed and time to determine. Okay, the speed that the person's going to be going at in the x direction is simply the x component of our VSL. Okay, once we determine the VSL, the x component we're going to use to find delta x, and the other thing we need to find it is time, right? Because speed equals distance over time. The time we are going to find from the y direction. So now it should be looking even similar to the earlier two-dimensional kinematics problems. Okay, so this is almost blending those two areas together. Okay, so first and foremost, let's find what VSL is. Okay, so VSL is equal to VSW plus VWL. Okay, so VSW we found to be 0,054 meters per second plus VWL, that's 0.45, 0 meters per second. And as we do with any other problem, you combine the x values together and you combine the y values together, because your final answer is going to have an x and a y component. So the x components added together, 0 plus 0.45 is just 0.45. And the y components, 0.54 plus 0, is just 0.54. So that's pretty straightforward there. Okay, and that's meters per second. Now, again, to find the amount that the person ends up downstream, we need the x component of VSL. Okay, so how do we find the x component? Well, first and foremost, we need, and this is going to be a lot of subscripts, but we need VSLX. So we've got two layers of subscripts there. How do we find it? Well, it's right there, right there. The nice thing about writing the vector in this format with the components is that you already know what they are. So this is VSLX, and you've got VSLY right there. Okay, so no further calculations needed. Okay, so we've got VSLX. We're trying to find delta x, right? That's our goal here. All we need is time, and remember, time we're finding from the y direction. So let's do that. Okay, now in the y direction, we're going to use the same idea, basic kinematics idea, that speed is equal to distance over time. We are not only going to reorganize this formula for time, so time equals distance over speed, but I'm going to substitute these variables in terms of y. Okay, so time is equal to, okay, the distance is going to be delta y, the change in the y direction, and the speed is going to be our VSLY. Now, the reason we can even do that is because based on the original diagram, okay, we're trying to find out how far downstream she's going to land. It's going to take a certain amount of time, and that time is given by the speed of the x component of this resultant. The y component of this resultant is going to take the same amount of time, right? Because x and y components always take the same time because they're relative to the same velocity. But we know that the y direction, the y distance it's actually completing is 77 meters. So we know the y distance, we know the y component of VSL, we can find time and then use that for the x. Okay, so time is equal to 77 meters over 0.54 meters per second. And when you calculate that out, you are going to get that time is equal to 143 seconds. Okay, although this is not correct to the right number of sig figs, it's okay because it's not our final answer. Okay, so just keep that in mind. Now that we've got the time, we can go ahead and use our x direction. So in the x direction, we use our same relationship. Okay, speed is distance over time. We're going to reorganize this for distance. So distance is speed times time. And specializing that for the x direction, the distance downstream is delta x. Our speed that's going to result in the downstream motion is VSL, comma, or subscript x, times time, and the time we just found over here. Okay, so our x component of speed is 0.45 meters per second. The time is 143 seconds. And when you calculate this out, you're going to get delta x equals 64 meters. Okay, so therefore, she will land 64 meters downstream. And that is the answer to part A. Okay, now I know you're probably thinking, wow, that whole thing just was for part A. Now we have to find part B, but you know what? One of the nice things in physics problems, and it's actually apparent in this one as well, is that a lot of times you solve for the later parts in the first part of the problem, depending on how you solved it. Okay, so part B asked us, how long will it take her to reach the other side? Well, we just did that. We just found how long it's going to take her. It takes her 143 seconds. So in fact, we have already figured out part B. Okay, so we already found the answer in part A to be 143 seconds. However, we need to express this to 2 sig figs, because our original problem is significant to 2 sig figs. Okay, so 143, if you give that to 2 significant figures, you're going to get 140 seconds. So time equals 140 seconds. And there is your answer to part B. So that's it for the video, guys. If you enjoyed it, be sure to click that like button and subscribe to Physics in the Flesh so you never miss a video from me. It's been a pleasure, guys, and I will see you in the next video.